TechDaily.ai, your source for technical information. This podcast is sponsored by Stonefly, your trusted solution provider and advisor in enterprise storage, backup, disaster recovery, hyperconverged and VMware, Hyper-V, Proxmox cluster, AI servers, SA365, a turnkey security appliance, and public and private cloud. Check out stonefly.com or email your project requirements to sales@stonefly.com.
Welcome to a new deep dive. We're jumping straight into the core of modern data handling today, exploring the evolution of storage tech, specifically NVMe and its network counterpart, NVMe-oF.
That's right. We got some really interesting material from you looking at how these work, how they're different from, well, what came before and where it's all heading.
Yeah, fantastic stuff. So we're going to trace that path, right, from inside a single computer all the way to these huge data center networks.
Exactly. It's a story about speed, definitely removing bottlenecks. But it also brings up new challenges, funnily enough, because of that very speed. Our goal today is really to break down this material, pull out the important bits, and help you understand why NVMe and NVMe-oF are, well, so significant.
Whether you're wondering why your PC feels faster or how data centers handle, tons of data super quickly.
We've got you covered. Okay, let's unpack this. So let's start with NVMe itself, non-volatile memory express. Why did we even need it?
Right, NVMe. It's a communication standard, fundamentally, but it was built from the ground up for non-volatile memory, which these days really means SSDs, solid-state drives.
Okay, built for flash. But didn't we have SATA and SAS? They worked with SSDs too, didn't they?
We did, yeah. But here's the thing, SATA and SAS, they were designed way back for spinning hard drives, HDDs.
Okay, mechanical drives.
Exactly. They were fine for that speed. But SSDs got so much faster, like exponentially faster. And SATA and SAS just became bottlenecks, serious choke points.
They just couldn't feed the data fast enough.
Precisely. Think of it like roads. SATA is maybe your county road.
Yeah.
Cheap everywhere, okay for stuff you don't need instantly, but slowish. And importantly, half duplex. Can't read and write at the same time.
Okay, one-way traffic, basically.
Sort of, yeah. SAS was better, more like a highway. Faster, point-to-point connection, full duplex, read and write simultaneously. Better error checking, too. That's why data centers used it a lot.
Right, makes sense. So if those are roads and highways, NVMe is like a direct flight?
Huh, maybe. It connects the drive directly to the CPU over the PCIe bus. That's the key difference.
No middleman controller like with SATA or SAS.
Exactly. It bypasses those older controllers, talks straight to the processor, and that just slashes the latency.
Latency, the delay, right, between asking and getting.
Yep. Super critical for how fast things feel. Maybe even more than raw transfer speed sometimes. But NVMe isn't just about that direct link. It was designed for massive parallelism.
Parallelism.
Doing lots of things at once.
You got it. Think about the older standard, AHCI for SATA. One command queue. You could line up maybe 32 commands in it. One queue, 32 requests waiting. Now, NVM. It supports up to 65,000 separate command queues.
65,000 queues.
Yes. And each one of those queues can hold up to 65,000 commands.
Whoa, okay, hold on. That's millions of potential commands waiting versus 32? That's not even comparable.
It's a completely different scale. It's built for modern CPUs with lots of cores and applications hitting storage all the time with tiny requests. It can just handle so much more simultaneously. Plus, the driver uses a different method, polling instead of interrupts, which also cuts down overhead.
Okay, so super fast, low delay, handles tons of requests at once. Where do we actually see NVMe?
Probably in the machine you're using right now. The M.2 slot on motherboards is really common. But remember, M.2 is the physical shape, the connector. NVMe is the protocol, the language it speaks over that connection.
Right, M.2 is the slot, NVMe is the tech. Good distinction. You also see NVMe in other shapes, right?
Yeah.
U.2 drives, AIC cards that look like graphics cards, even some standard 2.5-inch drives use NVMe now.
Gotcha. And the big question for many listeners, gaming. Does putting your game on an NVMe drive really make a difference?
Oh, absolutely, especially for loading times. Big games, loading new levels, starting up. It's way faster than an old hard drive or even a SATA SSD.
So faster loading, faster transitions, but maybe not frame rates once it's loaded.
Generally, yeah. Once the data's in memory or VRAM, the drive speed matters less for the moment-to-moment gameplay, but getting to the gameplay, huge difference.
Makes sense. And outside of gaming PCs, where else is NVMe critical?
Anywhere performance really matters. High-performance computing, definitely. Video editing, think rendering huge 4K or 8K files, DevOps, databases needing fast queries, and of course data centers everywhere.
Okay, so NVMe dominates for fast local storage inside one machine. But data centers are all about shared storage, right? Accessed over a network.
Exactly. And that's the perfect lead-in to NVMe, NFE, and over fabrics.
Over fabrics. Okay, so taking that NVMe speed and putting it on the network.
That's the idea. It lets multiple servers access pools of fast NVMe storage remotely, but trying to keep that low latency and high speed we just talked about. Think of it like ISCSI, which did network SCSI, but this uses the NVMe protocol end-to-end.
How does it work differently than local NVMe then? Sending commands over a network must be different.
It is. Local NVMe uses shared memory on the PCI bus, super efficient. NVMe-oF shifts to a message-based system. It wraps up the NVMe commands and data into what they call capsules for sending over the network.
Like little network packages?
Pretty much. And for identifying the storage, instead of local bus numbers, it uses an NQN NVMe qualified name. It's like an address for the storage target on the network, similar to how ISCSI uses an IQN. And you need network commands like discover and connect to find and link to that storage.
Okay, so it's adapted for the network. What are the big wins for using NVMe-oF?
Being able to separate your storage from your compute servers without losing performance is massive. You can pool all your fast NVMe drives together and let lots of servers share them efficiently.
Better resource use, easier management.
Exactly. Plus scalability. And it can reduce the CPU load on the application servers because the storage stuff is handled remotely. It's designed for scale, thousands of devices, multipathing for reliability. It's enterprise-grade stuff.
You mentioned fabrics earlier. What kind of networks, what fabrics can this run on?
That's a key part, flexibility. NVMe isn't tied to just one network type. The main ones are RDMA, Fibre Channel, and good old TCP/IP.
Okay, let's take RDMA first. Remote direct memory access. Sounds fast.
It is. RDMA lets machines swap data directly between their memory, bypassing the CPU and OS for the actual transfer. Think InfiniBand, RoCE, which is RDMA over Ethernet and iWarp. These usually give the lowest latency for NVMe because there's so little overhead. NVMe over RoCE lets you build a really fast SAN on Ethernet if you have the right network cards.
RDMA-capable cards, right? What about Fibre Channel? That's the traditional SAN network.
Yep, FCNVMe. It basically tunnels NVMe commands inside standard Fibre Channel frames. Huge deal for places already invested in Fibre Channel SANs. They can add NVMe storage without ripping everything out, and it can run alongside the older SCSI traffic on the same network.
So leveraging existing infrastructure, smart. And the third one, TCP/IP, that sounds like just regular Ethernet.
Pretty much. NVMe over TCP. This lets NVMe-oF run over standard Ethernet using the normal TCP/IP stack everyone has. The big win. No special hardware usually needed, like RDMA cards.
So potentially cheaper and easier to deploy.
Definitely more accessible. You can use it on basically any Ethernet network, even the internet theoretically, though latency would be a killer there. It makes NVMe usable much more broadly. And it's getting mature. You can even boot servers directly from NVMe-oF over TCP now with some systems.
Booting an entire OS over standard Ethernet from remote NVMe. Wow, storage really is becoming just another network service. How hard is this stuff to set up?
Well, it takes configuration on both ends. The host, the server, needing the storage, uses tools like NVMe-CLI. You discover targets on the network using their NQN and transport, like TCP, and then connect to them. On the target side, the system providing the storage, you use tools like NVMe-CLI to define which drives are shared, give them NQNs, say which network ports and transports they use, and manage access. You set it up, save the config.
So it's specific tools, but the concepts are similar to other network storage, setup, discovery, connection, access control, and the booting part.
Yeah, if the hardware and BIOS support it, you configure the network details and the target NQN right in the system firmware. Then early in boot, it connects across the network to find its root file system. The OS installer just sees it like another drive, maybe labeled TCP or something.
This all sounds amazing. Super fast drives, network access with low latency. Have we finally cracked storage performance? Are we getting everything out of these drives now?
Well, this is where the plot thickens, gets really interesting, and maybe a bit counterintuitive. The raw NVMe drives, phenomenal speed, hundreds of thousands, millions of IOPS per drive.
Right.
But when you put a bunch of them together in a big storage system, you often don't get that performance multiplied out. We saw an example. One drive hits 500K IOPS, but an array with 24 of them might only deliver, say, under 1 million IOPS total.
Wait, 24 times 500K should be 12 million IOPS. Why less than 1 million? That makes no sense. Where's the bottleneck now?
And that's the $1 million question, or maybe the 12 million IOPS question. When the storage media itself gets that fast, the bottleneck just moves. And right now, the big finger points at the storage software.
The software, the code running the storage array.
Exactly. The software doing RAID, deduplication snapshots, managing metadata, all that stuff. It often wasn't designed for hardware this ridiculously fast in parallel. It just can't keep up.
So the software can't process the data fast enough to feed all those super fast drives?
That seems to be the core issue. It's like having dozens of Formula One cars ready to go, but only one narrow pit lane exit. The software struggles to utilize all the hardware potential simultaneously.
Are vendors working on this? What are they doing?
Oh yeah, definitely. One way is just throwing beefier CPUs at the storage controllers. But CPUs are getting more cores, not always faster single cores. If the software isn't truly parallel, more cores don't help much beyond a point.
Okay, more cores need parallel software. What else?
Moving functions into hardware. Using FPGAs or custom chips to accelerate specific tasks like compression or RAID. That works for performance, but it makes it less software-defined, less flexible.
Trades flexibility for speed. Any other tricks?
Yeah, sometimes just limiting features, pushing some data services back to the applications running on the servers, which can work, but adds complexity elsewhere.
So these feel like workarounds mostly. What's the real fix?
The real fix, and it's a huge job, is fundamentally rewriting that storage software stack. Designing it from scratch to be massively parallel, to strike functions across many CPU cores efficiently, optimizing all the algorithms for low-latency hardware, it's a major ongoing effort for the whole industry.
Wow. Okay, so hardware leaped ahead. Now software has a big catch-up job. Speaking of hardware, NVMe HDDs, hard drives. I saw that mentioned. That sounds weird.
It does sound weird. Yeah, a prototype was shown recently. It's an engineering feat, no doubt, getting a spinning disk to talk NVMe. But the goal isn't really raw speed.
It's not to make hard drives faster.
Not significantly faster than, say, current SAS hard drives. It's more about protocol unification in the data center. If everything SSDs and HDDs speaks NVMe, it simplifies the software, the drivers, the management. It's about infrastructure consistency.
Ah, okay. One protocol to rule them all simplifies the software stack challenge you just mentioned. Makes sense.
Exactly. So don't expect NVMe hard drives in your PC anytime soon. That's a data center play, likely years away from being common, if ever, for consumers. SATA will stick around on motherboards for a while. Okay, wrapping this up then, what's the main takeaway for you, the listener? Whether you're building a fast PC or dealing with enterprise storage. Understanding NVMe and NVMe-oF shows you where the speed comes from, but also, crucially, what the current limitations and challenges are. Yeah, it really highlights that speed isn't just the drive, it's the whole path. The interface, the network if you're using NVMe-oF, and increasingly that storage software layer. The move to NVMe-oF, especially over standard TCP, shows storage getting more flexible. But that software optimization is the next big hurdle, which kind of leads to a bigger thought. You know, if storage hardware speed is being held back by software designed for older concepts, where else in technology might we see that? What other hardware breakthroughs are just waiting for software to truly catch up and unlock their full potential?
That's a great question to ponder. A lot to think about there. We covered a ton today, from NVMe basics diving into NVMe fabrics, the software bottleneck, and even NVMe HDDs. Thanks for joining us on this exploration. TechDaily.ai, your source for technical information. This podcast is sponsored by Stonefly, your trusted solution provider and advisor in enterprise storage, backup, disaster recovery, hyperconverged in VMware, Hyper-V, Proxmox cluster, AI servers, SA365, a turnkey security appliance, and public and private cloud. Check out stonefly.com or email your project requirements to sales@stonefly.com.